Welcome to the Waste video series. My name is Enrico Remigi and I'm the process modeler in the Waste development team. This video is a general introduction to Waste, our modeling and experimentation platform for water quality. If it's the first time you've come across Waste, or if you're unsure about whether Waste can answer your questions, then this video will hopefully give you a good general understanding of Waste and provide you with some good answers. In this video, I would like to cover the following topics. First, I would like to take you through a few case studies, which I believe are representative of the wide spectrum of applications that Waste can handle. We should then be able to better answer the question, what is actually Waste? And I would like to focus on the primary domain of Waste, that is domestic wastewater process modeling. And I will close off with a short demonstration of a dynamic simulation in Waste. Right, so let's take a look at some case studies. First case study has got to do with the implementation of a custom model, where by custom model, I mean a model that is not available in the standard Waste library, a model in this case for a chemically enhanced primary settling tank. The model was then integrated in a larger model and used to demonstrate to the client that they could actually save up to 30% on the chemical costs by changing the current operations. If you're interested in learning more about this specific case, you can download the leaflet from our website. Second application that I wanted to show is a whole plant model for the large wastewater treatment plant of the city of Warsaw in Poland. I thought this could be a good example of a complex process layout combined with an even more complex control layout. For this study, we had to implement some very advanced control algorithms. And here you can hopefully appreciate the overall result, layout. Intentionally, I left this spider web of red connection, red lines, which represent the control layer, so that you could, yes, hopefully appreciate the degree of complexity that you can handle in Waste without any problem whatsoever. A third application is a combined study of 4 small to medium-sized wastewater treatment plants in Denmark, where the objective was to identify alternative solutions to building new or expanding existing facilities. In particular, we proved that with a limited investment in new sensors and in a new managing system, considerable savings in energy, in chemicals, and in effluent taxes could be achieved, which resulted in just over a year of return of investment. Now, a completely different kind of application I'm showing you here, a customized graphical user interface on top of a Waste model of a municipal wastewater treatment plant in France. The Waste model was specifically aimed at simulating a novel aeration control algorithm developed by the client, and at verifying that this system would reduce energy consumption while ensuring the desired effluent quality and limited emissions of greenhouse gases. As you can see in this slide, the new graphical user interface, offers a limited access to the underlying model through this dashboard, which only exposes very few process parameters and allows for very easily and intuitively inspect the results of a simulation by selecting the desired tank or unit process in this aerial photograph of the plant, and then viewing the corresponding simulation outputs here on the right. This proved to be the ideal tool to deploy to the plant operator, to the plant staff for training. The last case that I wanted to introduce here is an application of waste to a completely different domain, a commercial washer laundry. The objective in this case was to support the client's water audit by identifying water-saving scenarios and thereby improving the overall water utilization. This study required a totally new set of models and a totally new set of icons to represent the individual processes. You see here, for instance, a washing machine, here a boiler, a cooling tower, and so on. Now, to summarize, and this was really the intention for this very quick overview of a variety of cases of applications of waste, is to come to a kind of a summary understanding of what is waste, what waste allows for. Well, waste allows for implementing new models of virtually any complexity. It allows for setting up complete wastewater treatment plant layouts, including the control layers, again, of virtually any complexity, and to carry out both process and energy optimization exercises. Last but not least, waste is a completely open tool. We've seen that a completely customized graphical user interface can be added on top of a waste model, and that the same modeling and simulation environment can be used or applied to very different domains other than municipal wastewater treatment processes only. And now let's try to define what waste actually is. Especially the last two examples required some degree of additional development. So let's now take a step back and look at what one can actually do with the standard off-the-shelf installation of waste release 2016. Basically, waste comes with two block libraries, one for municipal wastewater treatment plant processes, and the other one for what we call integrated urban water systems. It comes with three main working environment tools, waste itself, the model editor, and the block editor, and four licenses or commercial products. Waste for optimization, for design, for operators, and waste for automation. I kept these two groups separate intentionally. You will see it in a minute why. Now, when we look outside the fence of a treatment plant, then we talk about integrated urban water systems. In waste, we can not only model the processes, look at the processes that occur within the fence of a wastewater treatment plant, for which the base traditional block library is sufficient. But we can also look at compartments upstream to the plant, at the catchment and the sewer network, as well as the water quality in the receiving water body downstream to the plant. This is an overview of the models available in the model library of Waste Release 2016. You see a list of unit processes here on the left, and a list of what we call categories in the scope of waste, roughly corresponding to the ASM series of the International Water Association. You see that all the most common unit processes are present in the library, from buffer tanks, conventional activated sludge tanks, MBR, MBBRs, IFAs, and so on. And that besides the official activated sludge model series 1, 2, 3, and the ADM1, the anaerobic digestion model number 1, we also support a number of our own variants of these models. AN here stands for Anamox processes, a G1 and G2 for greenhouse gas emissions, PWMSA is a plant-wide model developed in South Africa by our development center in South Africa. Then I mentioned three main tools, three working environments within the full as part of the full installation of West. The main application for editing the plant layout and setting up and executing the simulations, West itself. The block editor for managing the library of icons. So if you need to add a new icon to the library, this is perfectly possible. And the model editor for managing the library of models. So again, if you need to add a new model or modify an existing one, this is also perfectly possible. And I've shown you a couple of examples, in fact, earlier. Model editor includes specifically two types of editing tools, a GUI matrix editor and the code editor, more traditional code editor. MSL is the language used to implement models in West. And then I mentioned four types of licenses for products available for West. The full license is called West for Optimization and allows for setting up and executing dynamic simulations, as well as what we call advanced experiments, sensitivity analysis, local and global, parameter estimation, scenario analysis, and uncertainty analysis. And also comes with the editors, block editor and model editor, that I've just mentioned to edit the model library. Then there's West for Design, which only allows for setting up and running dynamic simulations. And third, West for Operators, which is meant for deploying a model to an end user, will then only be able to execute the simulations, but not to alter the underlying model in any way. Something considerably different from these three first products or licenses is West for Automation, which is a software development kit which doesn't come with a graphical user interface and is meant for interfacing West, or better its engine called Tornado, with other components including SCADA. And here's an overview of the features that are included in the different licenses, but I've essentially covered all this already. And lastly, I would like to give you a quick live demonstration of West. Now, I'm not going to set up a plant layout from scratch. I have covered this topic in a separate video, which I invite you to watch for more details. Instead, I'm going to open this fictitious project that can perfectly serve my purpose now. Here's the layout of the plant. It's a conventional two-tank activated sludge system for carbon and nitrogen removal. First tank is non-aerated, the second tank is aerated, and aeration is controlled by a proportional integral controller. DO set point, this parameter YS, DO set point is 2 milligrams per liter. The influent, you can see it by double-clicking on the influent block. The influent is characterized in terms of flow rate and COD, TKN, TSS, and ammonia concentrations, but this list is not binding at all. This is just the list of measurements available for this particular example. And this is the graphical representation of the fractionation model, the translation of the set of measurements available, the blue blocks, into the state variables of the ASM1 model that is used in this project, the green blocks here. And then we have the two influent files that are generated by this influent wizard. A steady state file which is going to be used for the steady state simulation, average flow, we can see here around 22,000 cubic meters per day. And the second file is a dynamic file, which is going to be used for the dynamic simulation. Right, let's continue to explore the model. The temperature for the processes, the process temperature is set to, in this case, to 20 degrees. The volumes of the tanks are respectively 2,000 cubic meters for the anoxic, 4,000 cubic meters for the aerated, and 6,000, 1,500 times 4 for the clarifier. The flow rates of the three pumps, the pump for the recirculation of the mixed liquor, the pump for the extraction of the sludge from the clarifier, and the pump for the wastage of the excess sludge, are set to respectively 3 times the average influent, 66,000, 1 time 22,000, and 1.5, approximately 1.5% of the influent. Now, setting up the waste layout is very straightforward. Basically, all you need to do is drag and drop icons, blocks here from the block library, and connecting the appropriate terminals. That's really it. Very easy. I'm going to remove this, which I don't need. Right. Looking at the outputs that we can create in waste, here we have a sheet that contains a couple of plots: the oxygen concentration in the two tanks, the solid concentration in the aerated tank, and the effluent quality in terms of ammonia, nitrate, COD, TKN, and TSS, total solids. Now I could just launch the dynamic simulation, but for completeness, I'm going to start with the steady state simulation. The steady state simulation is essentially aimed at initializing the system. You can clearly see here that the biomass starts from a very low concentration in the two tanks and grows until it reaches a steady state of approximately between 4.5 and 5 kilograms per cubic meter. And similarly, the nitrification, let me hide this data series for now, and that nitrification and denitrification processes evolve also until they reach a steady state condition, a stable nitrification and denitrification. And finally, I can launch here the dynamic simulation, my 30-day dynamic simulation. You see that although with some variability, the oxygen is maintained around the set point of 2 milligrams per liter, that the solids in the tank are relatively stable, except in these two occasions between day 6 and 8, and between day 20 and day 22, where a considerable amount of biomass is lost due to two intense rain events, as you could easily see by looking at the influent file. As a final remark, I would like to draw your attention to two particularly useful features I find that have got to do with efficiently documenting your projects. Notes can be added to a project. These are rich text format documents that can be used to collect all kinds of information as you work through your project. Right, I'm not going to write much. I just prepared some text here. I'm going to copy paste just to show you what you can actually do here. And here we go. You have text, table, image, and anything you can think of in this rich text format note. And then we have reports, which can very easily be generated and in a completely custom manner. Here I have a new node, so I'm just going to select that item. Then you can look at generate the preview, and here's the preview of your report. And again, reports can be saved as a Word document, exported as a Word document to be further enhanced in a separate environment. And this was really it for this video. Thank you for taking the time to watch, and please come back for more videos. Thank you and goodbye.